All right, today is 2.5, linear inequalities in two variables. We have two vocabulary words, linear inequality and boundary line. Notice this is inequality. Okay, that's greater than, less than, greater than, equal to, less than, equal to. Equality is just an equal sign. That's not what we're doing today. Linear functions, which are linear equalities, that's the equal sign, form the basis of linear inequalities. A linear inequality in two variables, x, y, relates to variables using an inequality symbol, such as y is greater than 2x minus 4. Its graph is a region of the coordinate plane bounded by a line, either dashed or solid, and we'll get into that. The line is called a boundary line, which divides the coordinate plane into two regions, part of the solution or not part of the solution. Example, graph y equals 2x minus 4. The line divides the coordinate plane into two parts. So I just graph the line. I use the y-intercept and the slope, -4, and then 2 over 1. So this is the line, and it divides the coordinate plane into two parts. The first part is y is greater than 2x minus 4, which I'm just going to shade in blue. Notice shading, I'm not coloring it all in, I'm just drawing hatched lines. Okay, and how about y is less than 2x minus 4? This would be everything on the lower side. It's hard, but you can see you have a sloped line. You have an upper side of the slope and a lower side. Think of it as a mountain, above the mountain, below the mountain. And the boundary line is this, y equals 2x minus 4. That is the boundary line. Okay, let's try a few. Graph y is greater than or equal to 2x minus 4. Again, y-intercept of -4, slope of 2. Okay, I went down 4 and put a dot, and then a slope of 2 over 1. Up 2 to the right 1, up 2 to the right 1. I drew a solid line because it's greater than or equal to. And we're going to shade it. The solution, this graph is the solution, and it is your boundary line and the shading. That means that every point within this shading is a solution to that problem. To get that, every point within the shading is a solution to that problem. Now let's graph y is greater than 2x minus 4. Alright, I went down 4, and then the slope of 2 over 1, up 2 over 1, up 2 over 1. This boundary line is dashed because it's just greater than, so it's a dashed line. And the graph is shading everything above that dashed line. Okay, when you have greater than or equal to, you do a solid line because the solution includes the points on the line. When you have just greater than, it's a dashed line because the solution does not include the points on the line. It's just like when you would do a number line and you would put an open dot versus a closed dot. You know, this would be greater than or less than, greater than or equal to, less than or equal to. The closed dot's just like the solid line. The open dot's just like the dashed line. All right, example, graphing linear inequalities. Graph the inequality y is greater than -1/3 x plus 2. My y-intercept is plus 2, so I go up 2 and put a dot. My slope is -1 over 3. -1, positive 3, -1, positive 3, or I could do +1, -3, +1, -3. Okay, this is just greater than, so I do a dashed line. Again, you guys need to use graph paper and straight edges. And greater than, so I'm going to shade above my boundary line. And that is your answer. Less than -1, my y-intercept is -1. I don't have a slope, so I go -1 dot. Less than or equal to means a solid line. Less than means I shade everything below the line, and that is my answer. You try. Graphing linear inequalities. Graph the inequality y is greater than or equal to 3x minus 2. There you go. Y-intercept of negative 2, a slope of positive 3 over positive 1, or negative 3 over negative 1. I shaded up because y is greater than. Graph the inequality y is less than negative 3. There you go. Y-intercept of negative 3, no slope. Okay, let's try the next example. Graphing linear inequalities using intercepts. We didn't do this with equalities. We're going to do it with inequalities, though. We need to graph the line 3x plus 4y less than or equal to 12. Up to this point, you've been taught to change that into a slope-intercept form. Graph the y-intercept and then use the slope to find another point. We're going to try this a different way. We're going to find the intercepts. It's where the boundary line crosses the x-axis, which is the x-intercept, where y equals 0, and the y-axis, which is the y-intercept, where x equals 0. Okay, I'm going to change that to an equality, and we're finding the x-intercept, so I plugged in 0 for y. 3x equals 12, divide by 3, x equals 4. That's our x-intercept. Okay, now we're finding the y-intercept. So I plugged in 0 for x. 4y equals 12. Y equals 3. Save that for the next page. So we found the x and the y-intercept, where x equals 4 and y equals 3. We're going to go ahead and graph those. X equals 1, 2, 3, 4. Y equals 1, 2, 3. It's less than or equal to, so I want a solid line. Now, since we're not in slope-intercept form, I don't know which way to shade. Okay, this actually doesn't tell me if I shade up or down. So we are doing a test point. Plug a test point into the equation and figure out which way to shade. Okay, our test point is going to be 0, 0. Because it's really the easiest thing to plug into any equation, and you can use that test point for anything. 0, 0 is right there. That means I'm just going to plug in 0 for x, 0 for y, and see if my equation is true. Okay, 0 is 0 less than or equal to 12. Yes. So that means I need to include 0, 0 in my solution. So let's review what we did. Graphing an equation that's not in slope-intercept form. First, we found our x-intercept by plugging in 0 for y. Then we found our y-intercept by plugging in 0 for x. We graphed that line. Then we did a test point, and you can use 0, 0 every time, except if the line goes through 0, 0. It's not going to help you, but that's a rare occasion. So we're going to use 0, 0 for our test point. Plug in 0, 0 for x, y, solve it. If it's a true equation, if it's a true statement, include 0, 0 in your answer. If it's a false statement, don't include 0, 0 in your answer. Okay, you try it. Same steps. All right, there we go. I found my y-intercept, found the x-intercept, put in a test point of 0, 0 right here. That's our test point. Came up with a statement, is 0 greater than 12? No. So I don't want 0, 0 to be included in my solution, which is why I graphed down. All right, application problems. Many applications of inequalities with two variables use only positive values for the variables. Graph only the part of the coordinate plane that includes realistic answers. For instance, you can't have negative time. So you're only going to do the coordinate plane that is positive. Okay, time is not going to go negative, so you only use the positive part of the coordinate plane. A school carnival charges $4.50 for adults and $3 for children. The school needs to make at least $135 to cover expenses. Using X as the adult ticket price and Y as the child ticket price, write and graph an inequality for the amount the school makes on tickets. If 25 child tickets are sold, how many adult tickets must be sold to cover the expenses? It's a two-part question. Okay, we need to write and graph an inequality and then solve a problem. Okay, I want to point out to you that whenever you see at least in a word problem, it means greater than or equal to. Write it down in your notes, put it on a note card, don't forget it. So first we're going to write an equation. School carnival charges $4.50 for an adult ticket. And it charges $3 for a child's ticket. The school needs to make at least $135. All these problems are going to work out the same way. Okay, a number times a variable plus a number times a variable, an inequality, and the goal, what you're looking for. So we wrote an equation. Now we need to use the intercepts to make our boundary line. Find the intercepts so we can draw the line. $4.50 times 0 plus 3y equals 135. Divide by 3, y equals 45. Okay, $4.50x plus 3 times 0 equals 135. Divide by $4.50. X equals 30. So now we can graph it. Again, this is talking about tickets, so we're not going to use any negatives. Okay, graph the boundary line and shade. Pause for a second. Okay, making up your scale for your x and y axis is sometimes the hardest part. I just went by 5s. We already know that the adults are the x, the child's the y. The y-intercept was 45, and the x-intercept was 30. Okay, it's a solid line because it's greater than or equal to. And greater than or equal to means I'm shading everything above it. Okay, and think about this answer. We need to sell so many tickets to make at least $135. So everything along this line and everything above it, if we sell, say, 30 adult tickets and no children's tickets, 30 adult tickets, no children's tickets, we'll make $135. If we sell, this dot, which is 30 adult tickets and 35 children's tickets, we'll make at least $135. I mean, look at your answer and make sure it makes sense. If you only sell 10 adult tickets and 10 children's tickets, you wouldn't make enough money. Okay, if 25 child tickets are sold, was the last part of the equation, of the problem. I'll read it to you. If 25 child tickets are sold, how many adult tickets must be sold to cover the expenses? So it was $4.50 times adults plus $3 times children. Oops. Erase. Greater than or equal to 135. Solve it. Solving this equation for x, we get x is greater than 13.3, and I think that's actually repeating. You can't sell a part of a ticket, so you have to round up. Okay, think about your answer. So you need at least 14 adult tickets sold to make the money. All right, you try. Try it. Again, I'll keep saying it. Word problems, they get easier as you practice them. So a cafe gives away prizes. A large prize costs the cafe $125, and a small prize costs the cafe $40. The cafe will not spend more than $1,500. How many of each prize can be awarded? How many small prizes can be awarded if 4 large prizes are given away? So we need to do the same things as the last problem. Write and graph an inequality. Use that inequality to find out how many small prizes. Okay, the important part is here we have a different inequality. A large prize, the cafe will not spend more than $1,500. Will not spend more than means you're doing less than or equal to. It always seems a little backwards. So go ahead and push pause. There's graph paper on the next sheet. You'll see the answer, but I need you to work this out on your own. Alright, the first part is done. You have your equation. I found my y-intercept, my x-intercept, and then I graphed it. Okay, y is the large prizes, which which I graphed on the y-axis. X is the small prizes, which I graphed on the x-axis. Notice it's less than or equal to, so I shaded underneath. Oh, wait a minute. The last part of the question, so let's continue the you try. If 4 large prizes were given, how many small prizes can they award? Okay, so grab your equation and solve for x. Yikes. 500. Subtract 500 from both sides. I get 40x less than or equal to 1,000. Divide each side by 40. X is less than or equal to 25. No more than 25 small prizes can be awarded. Okay, the notes up here. We'll review graphing linear inequalities with your graphing calculators the first time I see you. I don't know if it'll be tomorrow. Remember, I do not know how to use the Casio calculators. I'm sorry. But I'll see you guys later.